Uh, Welcome to lesson 33 of the course on industrial automation and control. So, in this lesson we are going to look at DC drives. We will continue with DC drives, but we will look at DC drives which are supplied by a different kind of power source called switch mode converters. And then we will, once we do that and we understand how it works, we are going to extend the DC drives to what are known as brushless DC drives, which are very popular nowadays. So, we are going to first look at DC-DC converters and their operations. Then we are going to look at these DC-DC converter fed DC drives. We are going to look at their single quadrant, two quadrant operations. And finally, we are going to take a look at BLDC drives or brushless DC drives. So, our instruction objective for today are the following. So, first we will, after the lesson, the student will be able to understand the basic concept of how a switch mode converter works, what sort of a power source it is, and if it is connected across the armature of the DC motor, then what happens during its operation. This is the first instructional objective. The second is that, so once these various kinds of switchings go on, so we will see how the DC motor can be made to motor or it can be made to brake. So, that we will understand. Next is, we will also see that there are some kinds of drives which do not require which may not require all 4 quadrants, and so there may be a single quadrant drive requirement or there may be a 2 quadrant drive requirement, in which case it is not really necessary to have a 4 quadrant drive and we can simplify the circuitry. So, we will see them. The next one, and then finally, we will extend the concept of BLDC these DC drives to a new kind of motor called brushless DC motor, which does not have the disadvantage of the brush, but has the advantage of the DC motor, which is that the armature and the field fluxes are perpendicular, which leads to a very simplified control structure and also very good control sensitivity. So, we will see that how we can have the best of both worlds, obviously at the cost of increased electronics. So, now, we look at we first set off to understand this switch mode converter circuit, and here is a single phase switch mode converter. Sometimes it is this same circuit topology is also called a PWM inverter, because the same topology can be used to generate. In this case, what we are doing with this circuit is that we have an AC supply, which is our normal AC supply line frequency. Then we have a rectifier. So, a normal rectifier, constant, not a variable voltage rectifier. This is a constant voltage rectifier. So, some diodes, a bridge rectifier, along with a capacitor, a large filter capacitor, which, so these two together is basically constructs a constant voltage DC source. Let me choose a slightly thicker pen and white. So, constant voltage DC source. Now, this phase controlled rectifier is this not phase controlled rectifier, this switch mode DC-DC converter is actually produces, in this case it produces a variable voltage DC, which can be either positive or negative, and apply this variable voltage DC, bipolar DC, to the armature depending on the requirement of motoring or braking as decided by the speed controller, right. So, as we have seen that in a speed control loop, we are going to determine what sort of armature voltage we need to apply depending on our load disturbance or whatever, and these are typically used for servo drives. So, even if there are load disturbances, we want the speed to be constant or we want the position to be exactly accurately reached. These are the kinds of drives which are used in, let us say, CNC machines. Okay. So, we need to have a good control loop which will quickly accelerate and decelerate these machines. So, that it is going to do by controlling these switches. Okay. And why it is called, it is the same topology which is used in PWM inverters because of the fact that it is a bipolar topology. So, we can always generate positive and negative voltages. So, if we give our reference commands in a suitable sinusoidal manner, we can also get an AC out of it. The only advantage is that we can get a variable frequency AC out of it. If we use it in that mode, it will be an inverter. An inverter generates AC from DC. But in this case, it is being used as a variable voltage bipolar DC source, right. Remember, so first of all let us look at it. So, we have 4 switches which I have termed A plus and A minus and B plus and B minus, and with respect to and for in parallel with each switch there are 4 diodes. So, we have dA plus which is in parallel with the switch in A plus, dA minus in parallel with A minus, and similarly dB plus and dV minus. This DC source has this terminal as positive. So, this is the positive terminal of the DC source and this is the 0 voltage terminal. So, we are assuming that it is plus and 0. So, and these are the terminals which are connected to the motor armature. So, this A and B, here is the motor. So, we have the back EMF source which depends on the solely depends on the speed of the motor, then we have the armature resistance and inductance. So, as we can see that if at any time these switches are operated in pairs. So, we have either A plus and B minus on, in which case this terminal A is positive and this terminal B is negative, or we have B plus and A minus on, in which case we have the terminal B as positive if it is positive connected through this positive terminal, while this terminal A gets connected to 0 or ground or neutral, whatever you call it. So, you see, first point to be noted is that by making these switches on and off, we can apply either positive terminal voltage or negative terminal voltage to the armature. So, the voltages can be reversed. Now comes the question of the current. Now, suppose what is going to happen? So, now before we understand what is going to happen, we are going to see that in some detail. Let's take a look at the control law that we are going to use and then come back to the circuit and see what sort of voltages and currents will result. So, let us first see the switching law that is used, and then we will see that what kind of voltages and currents are produced in the motor in response to that switching law, and what will be its impact on the motion of the motor. So, that is the way we are going to see that. So, let us go a little bit forward and then come back to it. So, first of all, some simplifying assumptions. First is that the switches are ideal. So, we are going to assume that they are instantaneous turn on and off. There is 0 resistance, but the switches are unidirectional. You must remember that. In all other respects, it is like a switch, but excepting for the fact that we cannot have a current flowing in the opposite direction in the switch. These are the properties of these electronic switches, right. We will also assume that the source is ideal, that is the DC source is ideal, it has 0 internal impedance, and if it has 0 internal impedance, that is it has 0 regulation. So, whatever current is drawn, it is a constant ideal voltage DC source which can source enough amount of current that the converter may need, right. We are going to assume that, and it is to such that the source real source actually approximates that, we actually put all those filter capacitors, large capacitors. We will also assume that the inductors and the capacitors are ideal, so there is no loss. So, having said that, we will first note that the terminal voltage across the armature voltage is basically VA minus VB, right. So, we note that, and as we will see that in this circuit, the instantaneous terminal voltage and currents can be of either polarity. You can have positive positive, you can have positive positive, positive negative, negative positive and negative negative. So, they can be changed independently. It is not necessary that if the voltage is positive, current has to be positive. So, there will exist instants where all 4 kinds of combinations will occur. Sometimes you may also find that even if the switch is on, because of its unidirectionality property, it will not carry any current. So, while it will set the voltage, it will not carry the current. And we must remember that both switches in one arm can never be on, because if it is on, then the DC supply is going to be shorted by 0 resistance. Even if it is not 0, in practice it is going to be shorted by a very low resistance, and it will cause damage to the supply certainly. So, we obviously cannot have that as existing. So, now let us look at our our control law is that, let us go back. So, first of all, do not look at the rest of the diagram. So, first of all, let us look at the diagram up to this. So, only look at the top part of the diagram. So, what do we have? We have a triangular wave. So, this yellow triangular wave, right. This is a wave of a certain fixed frequency, right, a rather high frequency. This must be remembered that that this is a major difference with the line frequency converters, right. The line frequency converters always switch, the switches become on and off at line frequency, which is 50 hertz in our case. But here, as we will see, that the frequency of switching will be determined by this triangular wave frequency, which is generally much higher than the line frequency. It is of the order of several kilohertz. It could be 50, 100 kilohertz, I mean in some smaller converters or IC converters, but it can easily be 10, 20, 30, 40 kilohertz. So, it is about 1,000 times higher frequency than you have in line frequency converters that we have seen in the last lesson. Now, so we have a triangular wave which is of that frequency, and we have a control voltage which is a DC voltage. So, this is a DC, right, but this is the voltage that my controller keeps changing. So, this is applied by the speed controller, right. So, now suppose this voltage is at this level, right. So, what is our control law? Our control law is that whenever the control voltage will be less than the triangular voltage value, triangular voltage is continuously changing. So, at this point, let us say before this, the control voltage was greater than the triangular voltage, while from here up to here the control voltage is less than the triangular voltage. So, our control law is based on this relative comparison, and the control law says that if the triangular voltage instantaneous value is less than V control, then we are going to have A plus and B minus as on, and if it is not, then we are going to have A minus and B plus as on. So, let us see what happens. Okay. So, now we go back to our circuit. So, this is my triangular wave control strategy. So, you see that as we vary, let us note this, why it is also called PWM control is because of the fact that as you make the control voltage, as the speed controller makes the control voltage level go up and down. So, what happens is that you see that during this time A plus and B minus, rather A minus and B plus are on, and during this time A minus and B plus are on. So, whenever so you see that this voltage pulses. So, whenever A minus and B plus are on, VB goes to positive because B plus is on. So, VB will go to positive, while here A plus and B minus are on. So, VA will go to positive. So, by moving this we can vary the width of these voltage pulses, and therefore, it is called a pulse width modulation control. So, if we do this, then we can vary the average value. Remember that this is happening at a very high frequency. So, therefore, since the motor is a low frequency device, we must remember that the motor is a low frequency device. So a very high frequency voltage input is not going to have any impact on the motor. Only the low frequency part of the applied voltage is going to produce some motion. So, therefore, we need to consider the average value of these waves, and by changing these pulse widths we can make these average values go from a positive to a negative, right. So, this is what we are going to achieve. That is why it is called a pulse width modulated control, right. So, now let us see that how the voltages and the currents actually vary if we switch those, make these switches on and off like that. So, let us look at the circuit. Oops. Yes. So, now we are ready to see the voltages and current. So, initially suppose A plus and B minus were on. So, the current was, so the voltage was positive, the armature voltage was positive, and current was also flowing as positive, right. So, the moment, so what happens is that the current is positive, and also suppose that the motor is now rotating in such a direction. So, suppose the motor is motoring. So, if it is motoring, then we will typically have the back EMF opposing, the motor will be motoring when the average value is positive. So, for most of the time the pulse width will be such that on an average for more time A plus and B minus will be on. So, suppose that then the motor is rotating in the positive direction such that the polarity of the back EMF are as shown. In the motoring mode it will be opposing the applied voltage and it will be lower than that. So, there is a net current flowing, and the difference between VAB and EA is being dropped in the R and L. So, basically the equation is VA AB minus EA, this is the net EMF, is equal to Ri plus L di by dt. So, since this is positive, so therefore, L di by dt is likely to be positive and the current generally keeps increasing. Okay. So, when the current is increasing, then the current is as shown, by the white arrows, and the voltage across the inductor is also, this is positive and this is negative, correct. So, it is opposing the current. By Lenge's law, it will always oppose the current. Now, at this point of time, right, so this is going on for some time, and then in the meantime V triangular T has crossed V control level. So, at that point of time this will open, so this will become open and this will become on and this will become on and this will become off. Okay. So, suddenly now the voltage is reversed. So, now this is negative and this is positive, but as we know that current through an inductor cannot be instantaneously reversed. So, therefore, the inductor for a short amount of time, the inductor will, now what the inductor will try to do is it will try to maintain the current and it will instantly switch off its, change its polarities. So, it will now suddenly see the back EMF, still the motor is rotating in the same direction, rotation cannot be changed so fast at kilohertz frequency because it involves inertia. So, the motor is rotating in the same direction, therefore, the polarities of the back EMF are the same, but this inductor will now suddenly switch its voltages, voltage across the inductor will instantaneously change such that the current is maintained and it will still for short duration it will use its magnetic stored energy to drive the current in the same direction. So, the current through the inductor will keep flowing in this direction, right. So, it will go here. Now, this switch is off. So, therefore, previously it was flowing, previously if you have noticed it was flowing through this path, but now it cannot flow through this path. So, therefore, it has to, so what will happen is that because of the inductor will generate enough potential such that this diode will become forward biased and the current will start flowing in this path. And similarly, the current it cannot come through this path now because this switch is open. So, therefore, it will start flowing through these diodes. See that it cannot flow through this switch because this switch is unidirectional, right. So, in this switch current cannot pass through. So, therefore, even if the switch is on, the current will flow through the diode, and now to be able to sustain this inverse voltage and sustain the current, now the di by dt is it has to have a very large di by dt, right. So, the current is falling very sharply now. Now, at one point of time when the current falls sharply, then what will happen is that this current will actually fall to 0. Now, after the current falls to 0, then what will happen is that you see still this is negative, this is negative. So, after the current starts falling to 0, this VA minus EA we can assume that at the as far as the switching frequency is concerned, since the motor cannot accelerate or decelerate so fast. So, we can assume that at that switching frequency, if you consider one cycle of switching, then the speed of the motor remains unchanged. So, therefore, the EA polarity is going to stay same. So, EA is neither will the speed fall appreciably over one cycle, it will fall little bit. So, we can assume that this back EMF is also a constant voltage source. It remains unchanged in polarity and in magnitude. Okay. So, now once this armature inductance source has died down because the current has reached 0, now this VA minus EA will take over. So, this VA minus EA, now the current will reverse. So, now the current will start flowing through this switch. So, we can use this one, yes. So, now the current will reverse and it will start flowing through this, or rather no, it will actually start flowing through this path, and the current will reverse, and it will flow through this path. Similarly, exactly the similar thing will happen again when V triangular T will become less than V control. At that time again this will be off and this too will become on, and then again for some time the inductor will try to maintain the current in this direction. So, now the currents will, these switches will be on. So, the voltage will, terminal voltage will again be positive, but the currents will continue to flow through the other branch, that is the current will continue to flow, it will start flowing through this now. So, in that mode again the current will start flowing through this, it will still follow in the old path, but it will now flow through this and will flow through this path even if this switch is on, right. So, these are the situations that occur continuously at that 10 kilohertz or 20 kilohertz frequency. So, now we are, once we have understood that, so you see that there are situations where voltage is positive, but current has not reversed because of the inductor magnetic energy. If we watch it after some time, then current will also reverse. So, we have V negative, I negative. Similarly, we have the other situation. So, it is for this reason that we said that all kinds of combinations are found. And what will be the average effect of all these combinations entirely will depend on the pulse width. So, for how long which combination stays, we are going to have the net torque, the net voltage and the net current. So, everything will have to be averaged over long time to get the effect. So, now we go back to our waveforms. We have already seen these, yes. So, now we come to the waveforms. So, this is what is happening. So, the moment V control is, as long as V control is less than V control is greater than V triangular, we have A plus and B minus on. So, therefore, voltages VAN is positive and VBN is 0, B is at the neutral voltage. Similarly, the moment it crosses this, VAN goes to 0 and VBN goes to positive. So, if you see, if you want to draw the terminal voltage, then it will look like, so initially it will be VAN minus VBN, so it will be positive VBN. So, VAB, if you want to plot VAB, then VAB will go negative here, because it is VAN is 0 and VBN is positive. So, VAN minus VBN is going to be negative. So, now this white mark that I am drawing, so the terminal voltage VAB across the motor is going to be like this white mark. So, you see that what is now the average terminal voltage VAB? Obviously, it is VAN minus VBN is V, which is the VDC. So, it is going to be VDC, average is going to be VDC into T on divided by, so basically T on by T on plus T off. If I call this as T on and this as T off, so it is going to be VDC into T on by T on plus T off. No. Now, T off is equal to 1 minus T minus T on, right. So, it is going to be VDC into T on plus minus VDC into T off divided by T. So, it is going to be VDC, T off is T minus T on. So, therefore, into 2 T on minus T by VDC by T. So, it is 2 VDC into T on by T minus 1. This is the voltage expression, average voltage, right. So, what happens is if T on by T is half, then we have exactly 0 voltage. If T on by T is 1, then we have a positive VDC voltage. If T on by T is 0, then we have negative VDC voltage. So, this is the picture. Now, what happens to the current? So, look at this, that so the current was increasing during this time because of the fact that L di by dt, there was some net voltage which is applied voltage is positive, opposing back EMF is EA. So, VA minus EA is the net voltage which is being dropped across RA and IA. So, whatever is left is being consumed in the L di by dt. So, the current keeps increasing. So, the current keeps increasing. At this point of time, suddenly the switch is off in this point of time. Okay. So, immediately what is going to happen is now that now the inductor is trying to drive the current in the same direction. So, the current is still in the same direction, it is still positive, but it is rapidly coming down because the inductor is trying to, a large L di by dt is being created. So, di by dt is very sharply falling and it is overcoming the applied voltage and the back EMF. So, it is sharply falling. At this point of time it has crossed 0. So, during this time the diodes are conducting. So, during this time dA minus and dB plus are conducting during this time, this time. After that, for some time here A minus and B plus are conducting because current has become negative, and after that they are again being switched off. So, the moment they are switched off, now the current from negative it is coming, it is now rising. It is now rising, and you see that the two rates of fall and rise are actually different. Why? Because of the fact that in one case the di by dt has to be so large during this time the applied voltage and di by dt are actually of the same polarity. So, there has to be such a large di by dt that it can overcome that, while during this time the applied voltage and the di by dt are not of the same polarity. And then the current is at this point of time now, the current is, I mean they are here, they are aiding and here they are opposing, actually they are of different polarity, they are aiding during this phase. So, a large voltage has to be, current has to be driven against a large voltage. So, therefore, di by dt is falling sharply. On the other hand, here di by dt rise is slower. So, the current rises at this point of time, again from here the MOSFET or IGBT, whatever switches you have or thyristor, they will take over, and from here these thyristors conduct and the current again rises. So, this is the way that the current changes. So, what is now again you have to find, if you want to find the torque, you have to find the average armature current, and you can easily find out from that this is the 0 line. So, you can easily find out that the average armature current is actually positive. So, you are going to have a positive torque, right. That is because of the fact that A plus and B minus are actually on for a larger duration. So, current is positive. If you had made A minus and B plus on for a larger duration, that is if you have changed the pulse width T on by T off, if you had played with, you would have got a negative current, right. So, here the current can be reversed and the voltage can be reversed, and that is why you get a 4 quadrant control. So, this is the way these drives operate, and remember that these current switchings are actually occurring at, there are some other modes of the circuit which we have not discovered, like which we have not discussed, like we have current controls switchings which we are not considering even within one mode. But even then these switchings are occurring at very fast frequencies, and therefore the current ripples are really high frequency ripples, and therefore they do not have impacts on the motor dynamic, that is the motor motion, right. So, therefore, the torque ripples are much less. So, this is the way that, what is the matter? Okay. So, now there is also another interesting thing that we want to mention, that is it turns out that the armature voltage is actually proportional to the control voltage. That is very interesting. So, as we have said that V average AN is T on by Ts into Vd, Vd is the DC voltage. Similarly, V average Bn is T off by Ts into Vd. So, T off is 1 minus T on, rather T minus T on. So, you get this one. So, VAB, the V average across the terminal is 2 T on by Ts minus 1 into Vd, that is what we derived just now. And now let us, what is the triangular wave? The triangular wave, let us say any first part is nothing but, so there is suppose the peak value is V triangular, this is V tri. So, what is the time domain, what is the time function? So, the time function up to this, it is a triangular wave. So, it has 4 legs. So, we have to describe them by 4 different time functions. So, during this stretch the time function is V tri, this is V tri into at any point of time t, and this is Ts by 4. So, it rises from 0 to V tri in time Ts by 4. So, therefore, this is the time function for the triangular wave during the period t less than Ts by 4 greater than 0. During this time, this is the time function, right. So, I do not know why it is getting locked. Now, suppose we will see this, oops, yes. So, suppose at time t1 the triangular wave becomes equal to V control. So, therefore, this equation will hold, and therefore, this time once you are given V control and we are given V triangular, then this T1 can be solved from it, it is like this. Now, what will happen at if this is T1? So, now what is T on? You can actually, if you actually see, so this is T1 and this is T1, this is also T1, this is also T1. So, what is the time for during which sorry, so the time during which this stays on, see this T on is, this is T1, this is Ts by 2, half of the triangular wave. So, this is Ts by 2 plus T1 plus T1, this is the duration. So, the switchings occur here, here and here again. So, it is 2 T1 plus Ts by 2, and we know what is T1 is. So, we put just substitute T1, so we get this is T on. So, if this is T on, then what is T off? So, now V average T, we know what is V average T. So, we just substitute this value of T on. So, T on we just substitute. If we substitute, we will get this expression. So, you see in that V triangular is a constant, it is a design constant you have chosen, Vd is a constant, it is a DC source. So, this is that V average T which you apply across the motor is simply proportional to V control. So, just by switching up and on and off this DC voltage, you can apply a proportional average voltage to the armature. which can turn positive and negative. So, that is why this circuit is so popular, right. So, having said that, so this is that diagram that we were saying, that if current reverses, what will happen. So, we have already explained that, and these are the equations. So, EA is k phi omega m, torque is k phi into IA, and finally speed will be given by solving this differential equation, J d omega m. These are the equations of the motor. Standard separately excited motor equation, flux is assumed constant and unchanged with the variation of armature current. So, the equations are so simple. So, there are situations when IA is still positive but decreasing, then it is still accelerating. IA is positive means torque is still positive, right, and depends. I mean, net torque can be negative also. Similarly, if current is reversed but speed is still not reversed, then we are having, for the temporary duration, we are having deceleration. Now so this is the basic 4 quadrant operation. Now we look at simpler versions of this. For example, we look at 2 quadrant operation. If we have 2 quadrant operation, then we have only this circuit. So, you see that we are using only one arm. The previous circuit that we have seen, this is the DC source. We are using only one arm and we are connecting the motor across this arm. The other arm is fixed to the ground. So, then what happens is that now with this circuit, if you want to do motoring, so we do A on off and B off. So, B is off all the time. So, when A is on, the current passes through this. So, terminal voltage is positive and current is positive. So, motor is, so it will be motoring. If we put A off, then what will happen is that the current will still circulate through this for some time. So, we can control the, it will be falling, because now the L di by dt will change terminal and it will start driving the current in the same direction against the armature, back EMF. So, the current will be falling, but it will still be in the same direction. So, by controlling this, how long you are keeping it on and how long you are keeping it off, this current can be made to fall, and so the average value of the current can be controlled. Similarly, when you want to have braking, then A is on, A is off and B is on or off. So, when you have B as on, so then what will happen is that when you want to have braking, then A is off and B is on or off. So, if B is off and A is off, then it is still circulating, but the moment this is off, actually this then what will happen is that yes. So, when B is on, so after some time what will happen is that this current, when B is on, then what will happen is that for some time the armature inductance will drive against EA and the current will start falling, but it will still fall in this direction. After that, when the current comes to 0, at that time, or when the current becomes, when this current comes to 0, then this L di by dt effect will be not there, and then the motor EMF will start driving current through this path. So, then the motor EMF will be driving current through this path, and it may drive current through this path, or depends on this voltage. So, what will happen is that the motor electromechanical energy will get spent, because this basically this voltage source is actually generated by the motion of the motor. So, the motor will start slowing down. So, therefore, it will be braking. So, you see that, so you can see that you can still do motoring and braking in one direction, right, but you will not be able to change the direction of rotation of the motor, and therefore it is a 2 quadrant control. So, in one direction you can do motoring and braking. On the other hand, if you still simplified the circuit, you could have a single quadrant operation. So, for example, this is a very simple one in which you cannot even brake. So, you can only, if you switch it on, then the current will be flowing in this direction. If you switch it off, then there is no way that this so if you switch it off, then it will current will circulate, but still current will be in the same direction. Current cannot reverse in this case because you have not provided that switch. So, therefore, since this is a unidirectional switch, therefore, current cannot reverse. So, current can only be positive, and therefore, voltage can also be only positive. So, you have a single quadrant control. So, these are simpler versions of these converters. Oh, sorry. So, now we will quickly see, we have seen single quadrant operation and 2 quadrant operation. So, now we will see another, we will see the extension to what are known as brushless DC motors, which have permanent magnet rotors, right. So, now the armature is now, so now the field has come to the rotor, the DC field. See why brushes were required, because you wanted to feed armature current into the rotating thing. Whenever you have you want to feed current into a rotating body, you must have either a brush or a slip ring kind of arrangement, which is difficult to maintain, right. So, therefore, what we do is we change the places where we want to give supply. So, what we do is we now create the field in the rotor. So, we have permanent magnet rotors, and this has become highly popular after we have after there are some materials have been discovered which can create, which can have very high magnetic intensities can be created by these magnets. So, previously people used to use so they are not iron, they are actually made of some special kinds of material called rare earth. So, in the periodic table you have some rare earth elements, and these are made of these rare earth magnets are made of this rare earth, and they, for example, a typical one is cobalt samarium, and sometimes you have there is another version which is neodymium iron boron. So, these magnets can create fields which are order of magnitude larger than what can be produced with different grades of iron. So, now you fix these magnets on the rotor either as a surface magnet or which is on the rotor, or you sometimes when you have very high speed motors, then these magnets, fixing the magnets becomes very difficult, and they tend to fly away. So, therefore, sometimes you have interior magnet designs where the magnet is inside the rotor body. So, now now imagine that now these magnets, now you have a rotating field. As the rotor will rotate, you will have a rotating field in the rotor. You will probably notice later on we are going to do this, that's why they are sometimes, it is sometimes said that they are like synchronous motors, because in the synchronous motors, like what we have in all these power generators that are used in the generating stations, we apply DC field in the rotor. So, since we are also doing that using permanent magnets, so they are sometimes called, it is said that they are really synchronous machines. So, so now what is the problem? So, now the problem is different. The problem is that if you want to generate good torque, then the field in the rotor and the field in the stator must be perpendicular, then they will generate good torque. And if you want to have a simple control strategy, then they should stay perpendicular all the time. Now, in the DC motor, there is this brush commutator arrangement, the fields are fixed in space. So, the rotating field of the rotor in the DC motor by the brush commutator arrangement is kept fixed in space, and here just the reverse happens. Here what we do is, here we don't use a brush. So when we don't use a brush, our field in the rotor is rotating. So what we do is, by complex electronic switching and by sensing the rotor position, we also keep rotating the stator field. So now both are rotating. Previously in the DC motor, the field was, both the fields were fixed in space, they were not moving even if the rotor was moving. Now both the fields are rotating, but by cleverly rotating the stator field, I am always maintaining that perpendicularity. So while they are rotating, they are always remaining perpendicular, and therefore that basic property of the DC motor is being satisfied. Okay. So this is essentially why they are called brushless DC machines. So see, in this diagram we have this rotor which is rotating, and there is a sensor which senses the rotor position, and we have these stators. So the direction of the stator fields, now which stator, now you can see that by controlling these switchings, we can send current through these two, or we can send current through these two, or we can send current through these two. So by controlling the switching, as we have seen, we can send current through different combinations of stator fields, and therefore we can orient these stator fields in space also. So as the rotor is rotating, if we keep on changing the orientation of the stator field to maintain that perpendicularity, then we will get a control like that of a DC motor. So this is the principle. So you see that the various EMFs which are induced in the stator fields, now by construction they vary trapezoidally, because the rotor is rotating. So first the EMF in one stator winding, there are 3 stator windings. So there you see that they are 120 degree phase difference apart. So as the rotor is rotating, first this EMF is, so the EMFs across are actually varying with rotor angles like this. Now naturally, now if you switch your currents with reference to these EMFs, then you will get the DC motor like action. So you see that the currents are switched. For example, when is the A phase current switched? When the A phase EMF is full. When is the B phase current switched? When the B phase EMF, which is the green, is switched. So you see that you are always, if you see in the next diagram, so you see that during, this is the back EMF, this is the current you are driving again, and look at the other one. So at any 60 degree interval, this is the current entering and this is the current going out, this is 0, and during this, so during, when A phase is positive, so positive, while this is negative, right. So you are always delivering power into 2 windings. So if you see the next diagram, you will find that at any point of time you are delivering power E into I, which remains constant, into 2 windings. So you see, take any point of time, the total input power is always 2 EPIP. So here it is EPIP, here it is EPIP. So your constant power is being delivered, mechanical power is being delivered into the motor, and there is no variation in that, even if there is switching. So the motor motion is very smooth, right. So this is what is happening. This is the way the PM is controlled. So depending on the rotor position, you will have to switch on the corresponding currents, and then you will get torque. So this brings us to the end of the lesson. So what we have seen are basic operations of switch mode converters, and we have seen that how they can be used in drives, 1 quadrant, 2 quadrant, 4 quadrant, and finally we have seen the extension of these drives. So how this concept can be easily extended. We have not gone into, of course, how these switchings are realized and their analysis, so that will be too involved, but we have seen that how even without having a brush, by having a permanent magnet rotor and by reorienting the stator fluxes in space in synchrony with the rotor motion, we can get a DC motor like operation without brushes. Only thing we have to remember, that the price that we are going to pay for this are twofold. One is that we are going to have more complex electronics to be able to rotate the stator flux, and second is that we are going to require a position sensor. So, a rotor position sensor is necessary for this. There is of course a lot of research for other things, but as far as we know, a position sensor is required. So, that is all, and in the next lesson we will be talking about AC motor drives. Thank you very much. Welcome to lesson 34 of the course on industrial automation. Today we are mainly going to talk on, not mainly, solely going to talk on induction motor drives. So, we are going to talk on induction motor drives. The instructional objectives are the following. First, we will briefly see how an induction motor works, and we will try to see the principle of operation and the basic equivalent circuit, etc. So the student will be able to explain how an induction motor works. Then we will see that if once we know what the induction motor is, we will see what are the basic strategies of induction motor control, that is how we can speed it up, how we can break it, etc. Having done that, we will see how we will go to the technology side and see how there are two kinds of induction motor. Is an AC machine, so it uses inverters. So, we will see actually it can use various other things, but we will look at inverter driven induction motor drives, and we will first look at the square wave inverter, which is a simple inverter, and then we will look at the PWM inverters, which are more complicated devices but have advantages, and finally we will see how an induction motor, what an induction motor control looks like. So, to this end, first let us see what are the advantages of an induction motor. See, these advantages we are considering against what? We are considering vis-a-vis, typically vis-a-vis DC motors. So, what did we see in the DC motor? That DC motors have higher weight, their armature weighs more and costs more, basically because of the brush commutator arrangement, and so the induction motor has lower cost and lower weight.